Right, so this section is on, so let's see. We're kind of getting behind because, so I spent 2 weeks on surfaces. This looks like it's going to take 2 weeks also. And heat capacity, it's at least 2 or 3 weeks because there's a lot of stuff in that. So we might, I'm not sure. Anyway, the last two things are kind of extra subjects in a sense. And this is more or less a repeat of the beginning. So we have enough time, but basically we're going slower than in past years. So we're kind of spending more time on a few things for some reason. Anyway, so we're up to this enthalpy of formation. But the main point of the class is the heat capacity thing, like the Einstein and the Debye heat capacity equations, which that forms the basis of kind of understanding of materials, thermodynamically. So anyway, we have this chapter first, and then that'll take a little while. Anyway, so this is kind of I mean, surfaces was a little bit of a hodgepodge of different things, and this is too, in a sense, So the first anyway, so the first thing is just looking at the heat of formation, which is something you probably got in undergrad class in thermal, right? So you have like there's an enthalpy of formation and the free energy, Gibbs free energy. So it's delta G is delta H minus T delta S. So the difference between these two is the entropy. So if you so that and a negative number means that it's a good thing, or you're reducing the free energy. So negative is good. That means that in the ground state would be like the how the condition of the material is at normal conditions like atmospheric pressure, room temperature. It's like carbon would be graphite, and that's set to 0. So you have to have a starting point. This is enthalpy of formation from something. So from these ground state materials, it's like carbon, O2, H2, and nitrogen, N2, and then the ideal gases, halides, and things. So anyway, so it's basically, if you're going to make these materials, you start with those ground states, and then you'll add up the energy to create calcium carbonate from calcium metal at room temperature, and carbon and graphite form, and oxygen and O2. So it's like the delta from that state to this state at room temperature. So anyway, they're mostly negative because they're stable compounds. Anything stable is going to have a negative enthalpy of formation, or it wouldn't form, right? Except under some strange conditions. So if you have nitrous oxide, NO2, right, which is laughing gas, right? So that's got a positive enthalpy formation because basically it takes energy to make it, right? And the enthalpies, the free energy is larger than the enthalpy because the T delta S is delta S is positive. So you have so this number is negative, some number, this is some number like larger than that. So you have a positive, let's see. There's a positive delta S, and then that is negative delta S, sorry, and then that is a positive, so it adds, because you're going from a more random, like O2 is a gas to a solid, right? So, or something more organized, basically the entropy decreases. That's negative, and that's negative makes it plus, so it makes a larger, right? So if you're going from gases to liquid, like you take H2 and 1/2 O2 to go to H2O. So these are two gases, they have the entropy of gases, right? And then you go to a liquid, it's got a lower entropy. So this is a negative, usually a negative number, and that's additive to the delta H. So you get a smaller delta G compared to delta H because of the entropy change. So the difference between those two is the delta S, T delta S, and the T is like 298 Kelvin, right? So anyway, so that's that picture. Let's see. So that's that. So that's kind of like the first part of this chapter. It's more or less just following the book, somewhat. But anyway, so then there's this Ellingham diagram thing. It looks like a total mess. Okay, so you have this is delta G. So if you have this is for oxygen, like what would be the free energy of oxygen at some partial pressure? This is just the RT ln X kind of thing, Boltzmann probability. Pressure or the concentration would be the exponential of delta G over RT, like a Boltzmann probability. And so that's just the entropic condition for a gas, the free energy of a gas based on the entropy. Right? So anyway, so there's a free energy scale right here, right? So this is in kilojoule per mole, right? And everything here is based on 1 mole of oxygen and what else? Based on 1 mole of oxygen, it's a room temperature, atmospheric pressure. So you have these oxidation reactions. So usually you dig up a mineral and it's an oxide, right? And then you want to form the metal, like you want to get silicon metal to make wafers. Or you want to make titanium alloys, you need titanium metal. So you have to reduce it, you have to run these reactions backwards. Right? So each of these curves are in units of free energy of this free energy per mole of oxygen. So they're all oxidation reactions. So it's a reduction reaction when you go backwards, and oxidation when you go forwards. So anyway, so the slope is positive because most of them involve a gas going to a solid. I say you have silicon metal, solid, ground state, oxygen, gas, and then it goes to solid silica powder, like sand, basically. Right. So because of that, if you have H minus T delta S is negative, then this becomes positive, and you have a positive slope. Right. So except for if you do carbon and oxygen, which goes from carbon solid, graphite, and then oxygen's a gas, and you have to put 1 mole of gas going to 2 moles of gas. So that means your entropy is increasing. So that means you have a negative slope on this. So delta H is the intercept, and the slope is a delta S. This is T down here. All right, so that's, and then if you have the same number, say if carbon's solid, graphite, oxygen's a gas, and CO2 is a gas, so there's no change really in entropy in that. It's just an enthalpic. So it's independent. The free energy change is independent of the temperature for this forming of carbon dioxide. So normally, like if you're making steel, then you take like iron oxide. So you'd follow this iron oxide curve, or either one of these iron oxide curves. You want to run it backwards, and you're going to use coke to reduce it, to drive it backwards. So you need to know what temperature. So I'm going to mix coke in with iron oxide. And I'm going to try to make iron to make steel, right? So basically that would be like the standard metallurgy first thing you would do. So how would you get that? So you need to know for that reaction, both CO2 and CO are involved in it. So you need to know what you do is you find a magic CO2 ratio. So the CO2 ratio is like here. And then you're going to find like that ratio where you could get a reduction of the iron to make iron instead of iron oxide. Right? So that's one use of this diagram. So you have like 3 axes here. There's CO2, H2, H2O, and then there's this pressure of oxygen. There's 3 things. There's 4 things you can do with this. You can use if you're using hydrogen to reduce a metal to make a ground state metal from an oxide, this is going to give you what conditions you need to do that at, what temperature you need to do it at. And then if you're using carbon to reduce it, this will give you what conditions you need for the carbon. And then in general, so there's see, what else to say? So anyway, so these are the three things you can do with it. How easy, so if you're gonna, like there's something called magnesiothermal reduction. Magnesium's down at the bottom here, right? So it's the most easily reduced. So calcium would be better, but magnesium's the one that people use. It's like magnesiothermal reduction of titania to make titanium, right? Or of silica to make silicon. Right, say if you could make a silica that had a certain structure that you wanted, but in order to make it functional, like in a battery electrode, you'd want silicon. So you'd make your structure in silica, which is easy to do. In other words, you can make silica in a sol-gel reaction. So you take like SiO and some organic, this tetrahedral. This is called sol-gel. And then you can remove the ethanol and end up with just silica, which is SiO network. Same, right? So, but you can, this thing you can make into a gel and make a solid 3D high surface area, 1,000 meters squared per gram material, right? So, right. So, but basically, if you want to use it, say as an electrode, you need silicon, just Si, right? No O's. You have to remove the O somehow. You have to reduce it. So you can do that by mixing the two together with magnesium, and then because this is easier to reduce, magnesium metal will pull the oxygen off the silica, make silicon, and make magnesium oxide with some other byproducts of the reaction. But so you can use the plot to kind of just determine the temperature and see. This is the melting point. That's the boiling point. So the curves depend on the state of the material. The entropy change differs, right? So the slopes of these change, so they can cross. In other words, you can use magnesium to reduce aluminum if you're below 1300, 1400 C. If you're above 1400 C, then you can use aluminum to reduce magnesium, right? So it's kind of like the game is finding out where this is going to work. So that's kind of one part. The second part, if you're going to use, so you might want to reduce the oxygen partial pressure to some low number by reducing the metal, a pure metal, like titanium will eat up all the oxygen if you're in a certain condition. How much of the oxygen, so how far it goes. So these reactions don't go completely to the oxide and completely to the reduced. There's going to be some percent on each side. So depending on what temperature, you can pick out what concentration of oxygen you have in the system, which would be important as a control for an experiment. Like if you want to have no oxygen, you can never have no oxygen. So what percent? So the fraction, the atmospheres of oxygen, like 10 to the minus 50, 10 to the minus 100, some you want to absolutely get rid of oxygen. So you could use a metal, oxidize a metal to pull the oxygen out of an argon stream or something. And then carbon monoxide, yeah.
Understand how you like determine the pressure
Okay,
for
yeah. So this is how you do it. So you draw, it has these things, OHC over here, right? So I didn't mention that, but basically you pick the pressure you want to the minus 20 and you draw the line and connect it. Then say if you're doing like aluminum, if you want partial pressure minus 20, then you need to heat aluminum metal to like 1600 C. And then if you, yeah.
So the helium diagram is fully effective on oxide material, no sulfides plus oxide.
Yeah. Yeah, it's just oxides. I mean, you could make one like this for some other things if you wanted. Or I, these plots are all kind of old in the sense, but they're good as a reference. And people talk about it. But basically, you can do it with a computer program, and you wouldn't need to know what you were doing at all. Like you just say what condition, and it would tell you, right? So the plots are more or less before computers, in a sense, But in another sense, it kind of gives you a feel for what's possible and what's not possible. In that sense, that's kind of useful. Like if you say you wanted to make, so this is a pyrolytic synthesis, and you're trying to make a ground state metal from it, right? So of all the metals that you can look at, like which ones could you possibly make? Normally, when you burn something, you make an oxide. Like you burn ferrocene, you're gonna make iron oxide. You can't make iron because it's oxygen and it reduces it oxidizes it, right? But there are some conditions. If you have a reducing flame, it's possible you can just burn and make ground state metal. And the metal, because this is such a high energy situation, you're making nanoparticles. In other words, whenever you're far from equilibrium, so you're reacting organometallic, it blows up, it's an explosion in the flame. Like this thing, this is called a spray flame. This thing's going to be like a rocket engine. It's going to sound and look like a rocket engine. Like you need to wear goggles to look at this flame. It's like a blowtorch kind of flame, right? So that's really severe quenching, getting really high concentrations formed all of a sudden. Then the particles form, so it's really far from equilibrium. So the particles that come out of this are going to be really small, like 10 nanometer, maybe 2 nanometers, really small particles, right? So basically that's how people make particles, but a lot of times you want to have not the oxide, you want to have the metal. So what could possibly be made from that? So you can make copper, bismuth under some conditions. If you have, so these flames are typically going to be like 2500 C. So it's like 1500. That's easy to get in this kind of setup. So basically these metals down here, you can make, and then above that operating line, you make oxides, right? So then you can't get the ground state metal. You can't make like iron or manganese or chromium or cerium ground state metal with this flame, with that setup using, this is a mixed flame using carbon monoxide and hydrogen as a fuel. Like carbon monoxide's a fuel, you can burn it. I mean, it makes carbon dioxide, but so anyway, that's an example of like how you use, why we would use that. I mean, basically they're using it so they can calculate each one of these, but they can show like, oh yeah, well, you can't make these things, as a ground state metal. So it's a graphical tool to show like what's possible and what's impossible. And it kind of says like why, so that's more or less like in your mind, you have to formulate an experiment that you're going to do. And this is a tool to help you think about it, like what's possible, what isn't possible, and why. How could I manipulate this to make it possible? Like use a different fuel instead of hydrogen and carbon monoxide, use some other fuel that could reduce it. So anyway, so it's more like a way to think about what's going on. So yeah, things up above are reduced by things below, generally in the curve. So you want to find, so that's why carbon's used. It's like high up on the plot on this CO to CO2 and carbon to CO2. And then there's a carbon monoxide curve here too, somewhere. I don't see it, but anyway. So basically, the plot helps you tell kind of why you're using carbon to reduce things high up on this plot. And then, and like if you see a paper where they're doing magnesium thermal reduction, you know why they're doing it, because basically magnesium's at the bottom of this thing. So it can reduce anything up here, anything above it. It means you're taking magnesium metal and you're reducing silica, like an oxide, or any oxide above it, you could reduce. But all right, this is an expensive process because magnesium metal isn't that easy to get, and it's very reactive. Like it'll blow up. Right. So basically, anyway, it's the magnesium, even titanium is like explosive, right? So basically these things, if they're in a powder form, they're going to be like thermite, like they'll just explode, like thermite, you just put the powder on a steel rail, they use it to weld the rail lines together, and it just blows up and it melts them, right? So it's kind of made of magnesium and titanium, I think, mixture somehow. So it's basically like an explosive, or aluminum powder is explosive too. So basically they're in that action, they're like reducing the things, everything around them, but is it something else or?
Yeah, does it have anything to do with the chemical series or?
Yeah, yeah. Yeah, it's kind of the same thing, like oxidation reduction, but this is more for metallurgy. Yeah, so it's not for batteries. There's probably a similar plot for batteries. The same thing. I mean, it's kind of the same thing, like mapping out the free energy and figuring out what's going on. Right, so
Do you have like a comprehensive plot that shows the transition element, iodium, titanium, vanadium?
I think that the transition elements are more, well, iron's a transition element, right? So those, let's see, so it's a good question. I mean, I think this is the plot that I've seen that is there. It's mostly just reducing normal metals, not like, not things that are rare earth or something. I mean that, but you can draw your own because like you can just look up delta H and delta S, and then just make that plot. You can make it for anything you want. I think you can just put it, as long as it's one oxygen, you can put it any line onto this curve, and you can do the same thing with what partial pressures you need to do it. You can draw this yourself. Yeah, it isn't, so you can put any one that you want into this. These are like the common ones that are reduced. So
So does it work for, let's say, like KN4, K2, Sierra 207, and this kind of plot be used or something like that?
it would, yeah, I mean, this is just for oxidation here, but yeah, you could do it. I mean, it would be a different, yeah, it would be this. So you're not reducing with, yeah, this plot's like that. In fact, it's different. Like, is that, you mean an aqueous solution? So that's like a predominance diagram that you'd use if you do that in water, Is that what you mean, or?
Yeah, no, in this case, I'm having just one is like one metal reaction oxygen.
Yeah,
Actually, having like two metals, like KMNO4, like K2 Sierra 207, and like it's like two metals combining to, they're like more or less like they oxidized by just one, like just, how I say, two different metals. But now they're more or less like being oxidized, forming just one molecule.
hmm. Yeah, I mean that.
You need to look at
Each.
each
Oh,
of
Mhm.
the metals.
Okay. Okay.
Yeah, I mean, you can make that plot, if you want. I mean, this is just oxidation in these things. You wouldn't be looking at like oxygen partial pressure or these, see, you're looking at like, what are the competing reactions in this? So you'd have to plot what are the competing reactions. So you're trying to drive one reaction with another reaction here. That's the idea. So basically, whatever reactions you have, you'd plot them on this and you'd figure out, is it possible or not? And the slopes are different because the entropy change is different. So basically they can cross. You can see like the curves are crossing here. So there's a magic temperature above which you can get the reduction, below which you won't. The same thing would happen in your case, like if you drew the curves, they basically would be straight lines. This is kind of a assuming that everything is happening at room temperature too. It's like these curves, if you were going to go to a different temperature, you have to add in the heat capacity to this, like the integral of the heat capacity between the ground state, between whatever room temperature and wherever you're doing it. And that's not a linear function, so it wouldn't be a straight line if you were doing it at a different temperature. I mean, if it, there's a temperature change here. That's what's kind of confusing about this. There's also a heat capacity issue that isn't a linear dependence. So there's this business plus there's the integral of CPDT that you need to add to it. So anyway, this is how it's done for this Illingham diagram. I don't know if that's overlooked or what exactly, but basically they wouldn't necessarily be linear straight lines because the heat capacity isn't linear. So anyway, for what you're saying, like normally that would be done in an aqueous solution, and that's where you have these predominance diagrams, which are a little kind of along the same line as this, but a little bit more kind of, well, they aren't, it's an equilibrium diagram that tells you where the species are, where the predominant species are. So that's in some of the notes for somewhere that I kind of skipped over it. I didn't actually do that, but basically it's in the notes if you want to look at the aqueous stuff. It's kind of a separate subject, but if you're doing materials, a lot of times you work through an aqueous solution and then precipitate your things, you know. So the aqueous thing's a little bit appropriate for materials, but it's a subject in of itself, you know. Let's see, where is that? Let me just look for a second. That's in probably in phase diagrams at the end. The bottom. Yeah, here. So there's like 50 slides about, which I didn't go through, but it's kind of a little bit off track. Like these see, these are in water and they're predominant kind of ions that exist in water. How you predict which one. There's a whole thing to this kind of understanding of when you have different nitrates and acetates mixing together to form something else. Like so anyway, it's a whole thing to itself. If you want to look, it's like in the end of this section on whatever this was, phase diagrams, because they are phase diagrams. I mean, this other thing, the Billiam diagrams also phase, like this electrolyte business. I think it starts on 37 of that. No, actually it's before that. It's all the ternary, and then after that, predominance diagrams, and then that's the beginning of this electrolyte stuff. But it's a whole subject to itself that's a little bit off track. Anyway, so yeah, those are the three things you can do with this. You can get the partial pressure of oxygen if you're using like titania so you're running argon in, you want to have 10 to the minus 20 oxygen, then you know you need to heat the titanium to like 1600 C to get the minus 20. And if you want to have lower than that, then you have to heat it higher, basically. So you can kind of tool around to see where. And then this is for if you're doing like normal, like for iron, you're going to reduce it with carbon. So this is the CO2 ratio to drive the oxidation reduction reaction using carbon for like aluminum, say. That's also 1600 to get some particular CO2, like 5 times 10 to the minus 7. So those are the three things, like which one will reduce, what partial pressure oxygen will you get, and then what, if you're doing this carbon reduction, what the ratio of CO to CO2 you need to get it. Those are the three. And then if you're doing, and in this case, they're using water, using the hydrogen H2O, which would be the other curve here, like the H2O curve to get the condition for oxidation reduction in this flame, you know. So they're kind of widely used, you know, if you're trying to get ground state metals, which normally you want, they're more valuable than the oxides. I mean, because they're active, like for catalysts and things. Anyway, so that's one thing.
So how will we pick the point for del G here? Minus around minus 600.
The point, like it's saying that you want to get that what is the CO if you want to reduce aluminum, so you want to drive it, so what ratio of CO, CO2 do you need to do it? In other words, the more CO, the more it's going to be reduced. So anything above that point would reduce, and anything below it will oxidize.
No, I just wanted to know how they draw the curve.
The lines or the blue
The-
curve?
like,
You start with, if you're doing C, so it's just spec'd out for whatever, like if you're looking at oxygen partial pressure, use that point. If you're looking at hydrogen, water ratio, you take that point. If you're looking at the carbon, you take that point. It's just designed to do it that way. And then you draw a line from there to there, and that gives you your condition where it intersects the oxidation reaction.
Yeah.
It's kind of confusing, but it's just designed to work that way.
Yeah.
But you could figure out why it is that way, but basically it's designed to just use quickly, kind of get a number. You could write the free energies of the reactions and find out where the free energy for the carbon, the two reactions to make CO2 and to make CO, add the energies together, and then find the energy for that oxidation reaction. Then where they balance, that's where it works. So you can just do it all in equations if you wanted, but the graphic is easier, supposedly. It's similar, it looks a lot like a what's it called? A psychometric chart for humidity. Have you seen that before? It's almost as similar to this. Like you draw lines, you have the curves, free energy curves. Yeah, so it's kind of similar to that, but it's for metal oxidation. All right, is that good? All right. Anyway, so all right, so anyway, so this is just showing the add up the heats of formation. So you have different reactions to make this olivine, and then the olivine for this magnesium silicate can also form a spinel structure, which has this two metal sites in it. I think we talked about spinel before. It's got a tetrahedral and octahedral site. There's two different transition metals in it. And then basically that's the spinel. And then there's also a beta phase. There's three phases for this magnesium silicate. So they have slightly different energies of formation, right? So basically if you're going from beta to spinel, it's only 9.1 kilojoule per mole. And like olivine to beta is 29, and olivine to liquid's a little bit larger, but so basically they're all kind of similar energies. And then if you make the olivine from ground state magnesium, ground state silicon, then oxygen, then you get a big number because these things blow up. Like if you have powder, magnesium, and silicon, it's explosive. So there's a huge, but if you make it from the oxides, which are already have consumed some of that number, you just get a little enthalpy of forms, but it's a weaker energy of formation. Right. So the point of this is that to get these numbers, you just add them up together, like Hess's law. If you summon together the energies of formation, you had like you can just take the numbers from from that table, wherever that is. Like this table is from the handbook, and you can just look up the numbers and add and subtract to get the values that you need for this. Then this is from the book too. So it's like titania, which is TiO2. So it'd be like 66 would be like the normal condition for titania. But it's transition metal, and it can have all these different stoichiometries, right? And then it has like a minimum that isn't the TiO2 that we know. Right? It's like Ti6O11. It's almost TiO2, but not quite. It's got one too few oxygens. But the change is like nothing, right? 236.2 to 236.8. So it's a really small change. So basically, this is just showing that the heat of formation changes if you change the stoichiometry, which kind of makes sense. It's also an additive thing, like how much oxygen do you put in to make it, and the heat of formation. Basically, it's similar, adding up the enthalpies to get the enthalpy of formation. And then, so you have this, plot of, the bonds, which is in like every introductory materials book, I guess. So you have metallic bonds, ionic bonds, covalent bonds. And then if it's more electronegative, you form ionic materials, less electronegative, metallic or covalent. And then depending on how, the electronegativity difference between the two makes it become polar. So it becomes a salt, like an ionic. And as electronegativity itself increases, you get covalent. So metallic would be like low electronegativity for the components, and then low electronegativity difference between the things that are like a binary mixture. Right. So that's kind of like this, why you get ionic, why you get metallic. Ionic, both things are have electronegativity. Well, electronegativity, electropositivity, and the bigger the difference, you get ionic bonds. So the electrons aren't shared. Here the electrons are shared, and here the whole system's just a sea of electrons. So anyway, the electronegativity matters in terms of the heat of formation. Like these are going to have a high heat of formation because the electrons are pulled from one element to the other, right? So anyway, so anyway, let's see. I thought there was more on electronegativity here, but I guess not. There is later, but all right. So anyway, this is just showing Hess's law, like the adding up the energies. So these would have zero heat of formation, like a ground state metal, say oxygen or chlorine, Cl2 here. So it's making NaCl in this, but could be an oxidation. So the metal has to form a gas. I mean, conceptually form a gas. I mean, any route you take is okay to get to the salt. Right? So basically, you have to take the metal ground state and make a gas, and then you ionize the gas, so you get to an ion for the metal, and then you're going to for the halogen or halogen here or oxygen, you have to break apart the bond, get an independent atom, and then you have to add an electron to it. So then those two will form the salt, but there's also this energy associated with the lattice. Right. So I think the point of this thing is that there's this lattice energy. So you have these steps that kind of make sense, but even when you have the two separate ions, when they form the salt, there's something else added, something that has to do with the organization inside the crystal. So there's going to be ionic contribution, van der Waals interaction, dipoles. There's a slew of things that give rise to this lattice energy. So these energies are kind of, you could see you need that, and this thing's more mysterious, right? The lattice energy. So anyway, so the and the total heat of formation is going to be the sum of those things, right? And this one's kind of the complicated one. So that guy's going to have these components to it. Electrostatic, then there's a repulsion between the electrons and the atoms that are combining. This is just like Coulomb's law. This is a repulsion due to electron clouds. Dispersion is the van der Waals thing, which is kind of like if you have two atoms and they're coming together, and then the electrons are randomly moving around. So sometimes the electrons are on one side, so it'd be like a partial positive charge. So and sometimes the electrons in the other one are moving the other way, it could be partial negative. So that would draw the two together. And the force between two charges is q squared divided by r. So the distance is shorter when they're minus plus. If it happens to be that they randomly move around and it's plus plus, they move apart, then the distance is larger. So the force is attractive overall because the distance, because 1 over r, the attractive one is going to dominate over the repulsive one, even though they're both equally possible. So that's kind of the van der Waals dispersion force, kind of an odd one. And then in addition to that random motion of the electrons, they can also polarize. So there's polarization energy. So this is a random process of electrons moving around. This isn't random. Like once you get to, they have charged species like Cl minus Na plus, then this polarization of the electrons, it's an energy issue. And then this crystal field effect, which kind of has to do with the transition metals, which we'll have to talk about extensively. Right, so this thing becomes like why you get octahedral, tetrahedral, planar conformations for transition metals. Right, crystal field isn't for other things than transition metals, basically, unless you can dream something up. But basically, that has to do with the coordination number for the metals, like in the spinel, there's a tetrahedral and an octahedral site in it. The two of the metals that are involved in it are going to be in, the silicon and magnesium are going to be in tetrahedral and octahedral sites. So that means they're going to have different crystal field effects that add to the energy. So the energy of the two metals depends on if they're tetrahedral, octahedral, or planar bonding. So that's why so there's a whole part in here about transition metals. In the book he just skips over, which I think that it takes a little bit to look at it. Anyway, so looking at this, like breaking it apart one by one. So electrostatics, Coulomb's law, so it's Q squared, it's Q of each of them, and then divided by R. 1 over R gives you the electrostatic part. And then that's the simplest thing if you have just two ions, but in a crystal you have like face-centered cubic NaCl, you're gonna have like NaCl, Na at the face center and Cl at the corners. Looks like if you look at one side of it, it's like that. Yeah, you have like minus and plus associated here. We also have these Cl-Cl interactions too. So it's like that one, and this one's 2. And if you go to the next crystal, it's going to be another Cl. So there's another. So you add them up in series, like first neighbor, second neighbor, third neighbor, right? And it's going to go plus minus if it's a salt. So you have like plus minus, plus minus, plus minus. All of them are going to be the same Q. Or the charge on the Na and the Cl are the same. So Mx doesn't really matter, it's just Q squared. Then the R is the distance, and the R distance changes according to like, this will be like the lattice parameter, and then like this is the factor that it changes that. And E is the charge of the electron. Right, so see, that would give you this electrostatic interaction thing becomes a more complicated number because it's got this infinite series. It goes on forever, right? So you call that the modeling constant, this infinite series, and you just have modeling constant and then number of atoms in the unit cell, and then the Q's and the R gives you the electrostatic thing. So that's the first term. And the second term, I mean, how important this is, I mean, basically it's just to kind of look at it. I mean, you might need to use it in some particular circumstance, but it isn't like you have to memorize a modeling constant. You know what I mean? It's just like the basic idea is just to give you a feel for what's going on. So these two are coupled together, the repulsion and the dispersion. That would be like the 612 potential, which is this Leonard Jones. This is the guy, so the guy's name was Leonard and he married a woman called Jones and he hyphenated his name. So weird. And this was in the early 1900s. It's kind of odd, right? I mean, anyway, even nowadays, I had never seen that actually, but that's what Leonard Jones, it's not two people, it's one guy. Hyphenated his name. So anyway, so the 12 is a repulsive, and this 12 part is just kind of a made up, and van der Waals calculated the 6 part. So the 6 part is this idea of the charges randomly are associating, dissociating. And because the opposite ones pull together, then it ends up being an attractive force. It lowers the free energy. And this is a repulsive force, and it's just a function that they picked that worked, the 12, or he picked, right? And then in ceramics, they use this Buckingham potential. So the random part they say is an exponential instead of 12. But they're both almost the same functionality because it's a short range interaction. And it just drops off. So basically, both of these drop off quickly, right? So anyway, so basically that the 612 takes care of the two repulsive dispersive. So a lot of this would be like in computer simulations of crystals too. Like you, in other words, you're going to pick up the LAMPS program to simulate your crystal. You're going to say, what are the energies of interactions of the atoms in my crystal, right? I mean, you can do crystals in LAMPS. And then say you're going to anneal silicon crystals, you want to see the grain boundaries disappear or something, and it's computer simulation. So you set it up so it's got a grain boundary, the atoms are all in a crystal. Then you need a potential function to work on how they're gonna, like, is the atom gonna randomly move by KT? Then these potentials are gonna make it like move back, right? So all these terms would come up if you're doing a computer simulation of a crystal. You'd have to specify each one, but basically you would Google and someone else would have done it and you'd figure out how to do it that way, right? So, and it, maybe a few people have figured it out from the beginning, but almost nobody. Everyone would be like looking at how other people did it. So anyway, so 612 is a common thing to plug in, and you can also plug in the Buckingham potential. That's also pre-programmed into the LAMPS thing for sim. There's other simulation, but LAMPS is the one that's easiest because it's most used. Then the others, let's see, what else? The polarization and the crystal fields for transition metals and the polarization. He just shows the this business about how electronegativity impacts the lattice energy. So total lattice energy, how it's impacted. Again, like the lattice energy is just the one component of the whole free energy of formation. So you have free energy of formation is going to be like the sum of all these separate things, which probably are larger than the lattice energy, and then this lattice energy. So he's looking at just that part in this book, part of the book, and then this just the electronegativity part, the polarization. So the more electronegative you get, more lattice energy goes higher. I mean, that kind of makes sense. And then if you have electronegative, so it's an alkali and a halide coming together. So basically, the less electronegative the alkali, the lower the lattice energy also. So this is just a term that adds in. So electronegativity kind of decides the polarization term. That's kind of what's going on here. And then this C is this is the components of that associated electron gain part of this thing. That's a separate part of the free energy, right? This business. E.g. electron gain and ionization, right? Those two things, he's just showing a plot of how that changes with which halide you're looking at. And there's no change. So I don't know exactly the point of that, but that's just showing that they're flat. And then oh, this is across the halides and this is across the alkalis. Right, this electron gain, these are the two steps, dissociation, electron gain, then ionization and atomization. So atomization is vaporization of the metal, and ionization is making an ion out of it, making it a positive ion, removing an electron. Right. So I think he's just trying to show the relative contributions to this lattice energy, and how they differ for the different systems. There's not much more to get from that, I think. At least I don't know more than that, but and then all right, so formation for the alkali metals. Yeah, these are just trends, that, I mean, you can look at it. This is showing this is showing how the transition metals, so he's going across enthalpy of formation, and he's looking across, so it's all Cl2, and then it's across the, he's going down the, let's see, beryllium, magnesium. So he's going down the group, down the group of the second group metals, right? So And then he gets here to magnesium, and then he goes to the transition metals. So he switches from here to the transition metals. And then this continues on the second group. Right, so he's saying that the transition metals have a higher enthalpy of formation, which has something to do with and it happens both for let's see, it happens both for the chlorides and for the fluorides, right? So that the transition metals have a higher heat of formation that has I think he's showing that this has to do with the last term in this thing, the crystal field term, which comes up with transition metals. So something else happens with transition metals. It doesn't happen with the straight metals that don't have multiple oxidation states, right? So all of a sudden, if you go down the series and then click over to the transition metals, you get a higher energy of formation that's associated with this crystal field term. So basically, the crystal field term has to do with how the chlorine interacts with the electron structure of the transition metals. So there isn't just, so depending on the electronegativity of the fluorine or the chlorine, then you'll get a different electronic state for the metal, and that shifts the energy of the crystal, energy of formation. So the transition metals have a special relationship with their partners when they form binary mixtures, or even if it's a multi-component, right? So anyway, so the transition metals are these kind of d orbital. So you have s orbitals and p orbitals. So you're filling up the orbitals, right, with electrons. As you're going across the periodic table, you get more and more electrons, so they fill up the electron orbitals. So 1s, 2s, 2p, then you form 3s, 3p, 3d. Once you get to d, you're in the blue part. Then you have the d orbitals, right, which have different states that are possible depending on what the binding anion is with the metal, right? So depending on the kind of the electronegativity of the binding group, the coupling with the metal. And so that's kind of the idea of this crystal field theory. It's like the idea that you can predict these structures, right? So this is showing, there's books, and there's also some web page on the linked up that you can read about this if you want. But anyway, so basically you have a metal cation. If you put the electrons around it, then it could make a spherical shell if it was isolated, right? And it's going to have some energy. So this is the energy in the y-axis. And then if you couple it with if you bond it with the anions, then it can form different it affects that electron shell. So that electron shell turns into these orbital structures, right? So they're going to become things like this. Okay, so basically this is an octahedral. So you have 6 anions coupled with a metal atom in the middle, and the electrons in the d orbitals can form these 5 different configurations. So like quantum mechanics will give you these structures. Like you do a calculation, you can figure out these structures. Okay, so basically these are calculated structures. So depending on the strength of the anions, the energy of these different structures are different, right? So basically, if it's in an octahedral configuration, so there's 3 options. It can be octahedral, it can be tetrahedral. There's a picture of that somewhere here. Octahedral. That's also, tetrahedral is kind of the middle here, but this is planar. That's square planar, and tetrahedral is like here. So basically, these same orbitals, depending on the configuration of the anions around it. So tetrahedral and octahedral both have 6 anions. And then planar has 4. It's got 4 anions per metal, right? So basically, the way the energy of each of these states, so it's going to split the energy. So you have the average energy if it was spherical, see wherever that is. And then that energy is going to split into these orbitals. Each orbital is going to have a different energy. Then there's this transition energy. So if you have an electron in the bottom orbital, you can shine light on it and it'll go to the upper orbital. And that absorbs light at a certain frequency related to that energy. That means it'll have a color, like that metal will have a color associated with that energy. So H nu is the energy, nu is the frequency. That's the frequency of the light that it would absorb. So the transition metals can have these color features that basically associated with this. If it goes from octahedral to tetrahedral, the color changes. Right? So that depends on what the anion is. It's pulling on the electrons, pulling on the electron clouds to give different energy states for the material. This is because it gives a color, it's called a spectrochemical series for the anions that are attached to it. Like this is a spectrochemical series and lowest to highest energy, and it doesn't necessarily follow any logic sequence. There isn't a logical reason why it's in that order. Like it isn't like one's more electronegative than the other. It's just the spectrochemical series, right? So basically, once you know what that is, and you can kind of figure out what which state, octahedral, tetrahedral, planar, that the transition metal will go into. All right, and again, that's going to affect the heat of formation. It's a long story to get to like a number that you get out of it, right? So, I mean, the importance is that these transition metals are in like all, I mean, life is based around it, like iron and hemoglobin and magnesium, and everything is involved in life actions, reactions. So basically knowing this kind of structure impacts directly life. Also, catalysis is going to be totally based on transition metals. So transitioning from one state to another is going to be what drives a catalytic reaction. And then, so if you're making catalyst, this is like the main meal, right? This is transition metal, like the main thing you're looking at. You want to form like complex crystal structures where you can have metals in different states so that they can transition from one ionization state to another, and that drives a reaction, some kind of reaction, right? So oxidation or something else. But so anyway, so you have the average energy. If it was an ion and then you add the electrons to it, and then it has a certain energy, and that energy splits into these two different states if it's in an octahedral. I mean, two different energy levels that are composed of 5 states, right? So 5 electron clouds, and then depending on how many electrons a transition metal has in the d orbital, it's going to fill up these states. So it'll start filling up like 1, 2, 3, and then it'll, depending on the strength of the anion that's attached to it, it'll go 4, 5 if it's a weak anion. If it's a strong anion, it'll go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like two for each orbital, right? So the anion is going to decide how it fills these. And if you have unfilled orbitals, it's paramagnetic. So it'll react to a magnetic field. And if it's filled orbitals, then it's diamagnetic, and it won't react to a magnetic field. This has back to do with the magnetism too of the material. Right. So one way to test if you have filled or unfilled orbitals is, does it respond to a magnetic field or not? And also, again, like if you shine light on it, whatever the energy gap, this octahedral energy gap is, then you can get the light absorption color that, like, it'll absorb the ones that it doesn't absorb is the color that you see. It's going to subtract color from the white light to make it colored light by the length of that gap. Yeah.
But they'll,
That's the energy of transition.
so it is not band gap.
No, band gap is something different. This is the transition, octahedral transition energy. Oh, band gap is it's something different.
Yeah.
Yeah, it's for it also absorbs photons. that's the electrons.
Band gap is the.
This is kind of for an isolated atom, you know, I mean, in a sense, it's in a crystal, but basically this is the electronic structure of one atom. And a band gap is when you have overlapping orbitals, and then there's like it smears this out. And then you get energy levels due to the clustering, like whole metal, like a whole metal, right? That's a semiconductor. So this is different than band gap. This is more like one atom. So when you're looking at a catalyst, they don't usually look at band gap. It's more like if you're looking at like electronic properties for electronic devices and for solar cells. So in my mind, they're different. I think they're different. They're separate. I mean, there's no orbitals. That's in a metal, that's in like a cloud. I mean, it's different. So there's no, all right, this is almost like the first step towards that. Like you have a pure metal, then it has a band gap. Then you have, this is when you have a binary coupling, you have an anion and a metal, and it's a transition metal, and it's similar, you know, but basically the different, totally different subjects.
It just, yeah, and also band gap is the distance and this is energy, so. Yeah.
No, band gap's a distance and energy between an occupied and unoccupied level, right? Like a Fermi level, and so, but it's along the same line, you know, I mean, they're all energies. It's all got to do with electrons, but this is for a specific case of a transition metal with an anion on the side of it and how it changes the orbitals. Like in a band gap, you don't have orbitals,
Yeah,
right? There's no orbitals. It's like kind of yeah, it's a shell. It's different. It might just be that the way they looked at it was differently, and it might be the same thing. But basically, this is kind of different because you're talking about is chemically manipulating this. So this is where like materials and chemical inorganic chemistry kind of come together. You know, so they aren't. This is really vital to a lot of materials problems people are doing. But it's also like all the theory of it comes from inorganic chemistry. So like if you want to find this stuff, you're looking at inorganic chemistry book. But probably like of the people that are like publishing in Nature of material science, probably like half of them are doing stuff like this. Like this homework this week is like MOF, which is like a hot topic in materials in like Nature in science, you know, and they're doing, this is what they're doing, but it's really inorganic chemistry. All the theory is back in inorganic chemistry. How you manipulate it and make something with it is kind of materials. And there isn't a clear distinction between the two. So in the catalyst people, the kind of chemical engineers are doing the same thing. So they're all like coupled together. Yeah, it's a little confusing. And the band gap thing's something separate. That's like electrical engineers and also materials. But we'll talk a little bit about, we'll talk about band gap when we talk about heat capacity. So it's kind of coupled with that, you know, like density of states and things. This isn't density of states. It's weird. It's the same subject kind of, but they're separate disciplines, you know, so they aren't necessarily connected together. But all right, so anyway, it's a good question. Anyway, so this is just showing that you can get an absorption band. So you're doing spectroscopy. So this could be Raman or IR spectroscopy, and you see an absorption band associated with this transition. Or I guess this is visible. UV vis, right? Probably. And then you see this transition basically, so you can measure that number. Like you can put your material in, stick it in the UV vis spectrometer, get this peak, and that peak position, it's a frequency, you can convert that H nu as an energy. So you can actually measure that energy. And then you can measure the energy. So you can have a transition metal in a crystal and it can transition from an octahedral to a tetrahedral state due to light shining on it. So you can also measure the transition from octahedral to tetrahedral setup. So when you get to tetrahedral, So this is all octahedral. And this is just showing the octahedral energy, how it depends on what the transition metal is in it. And then this is the tetrahedral. So you can get an octahedral to tetrahedral transition. The del T is smaller than the del O. And there's a fixed relationship between the two. So if you measure transition from octahedral to tetrahedral spectroscopically, and you'll get this 0.44 from that. Like basically you'll get the difference between del T and del O if you get a transition between those two. Anyway, so it has to do with the organization of these. So the anions, let's see, the black are the lobes of the no, this is just showing the tetrahedral and octahedral positions, right? And then these are all done in X, Y, Z, like Cartesian coordinates. So they fit into this. So it depends on the proximity of the electron cloud to the anion, right? So if electron cloud is aligned with the anion, that's a high energy because you have negative, negative, right? And then if you have electron cloud like catty corner to the octahedral anions, then that's a low energy. Like XY is lower energy than X squared minus Y squared. So you kind of graphically see why one's high energy, one's low energy. And it's the same way with the tetrahedral. So the octahedral is that, and the tetrahedral, I guess, is the black ones, and it just shifts the positions of the anions with respect to the orbitals, and that's why you get this shift in the energies. So it's all geometry. It's like all just geometric, moving around the anions with respect to the electron clouds gives you these energy transitions. And the other option is this planar complex, right, which has some more complicated association of the electron clouds with the anions. So it looks like that. So that thing is going to be higher energy, so that the tetrahedral is lower energy gap than the octahedral, and the planar is higher energy gap, 1.74. So this just shows like kind of a transition from octahedral to planar, how that would transition in a metal. So this is like all right, so this is so if you have iron chloride, right, ion, then the iron's in the +3 transition state. So it has, so if you figure out that iron is let's see, iron's 26. So if you start adding up, like 1s be like 2, 2s would be 2, 2p would be 6, fills with 6 electrons, 3s is 2, 3p is 6, and then you have the d orbital. So if you add those up, 26 minus 3 is 23. You'd only have 5 left for the d, right? And there's 5 energy states in the octahedral, so it would fill up each of the states if you have a weak anion with it. So chlorine, you would look at the spectrochemical list, wherever that is. Here's the chlorine's at the low end, so it's a weak anion. If you were coupling with nitrate or cyano group, then it wouldn't fill up like this. Oops, wherever that is, 30 here. So because chlorine's weak, it fills up 1, 1, 1, 1. If it had been Cn minus, it would have been like 1, 1, 2, 1. Like, so this is a paramagnetic, and that would have been probably a diamagnetic material if you did the Cn minus. Right, so you can kind of see how you're going to use this orbital mapping, of the energy mapping for the orbitals, and you're going to like figure out how many electrons you have and fill it up, and then see what kind of behavior you'd get from it. All right, so that's one part of this. Then So, so if you have these are like problems, right? So if you have a tetrahedral complex, absorbs at 545 nanometers, and then you can calculate what the energy of that is, right? So you can calculate this tetrahedral transition energy, 545 nanometers to meters, and then H, that's the value, and then C, that's the value. And you just get the energy, 3.65 10 minus 19 joules. And then what is if you're going to transition from tetrahedral to octahedral, what color would it be? Right, so you say there's a relationship between those two, so it's 0.44. Octahedrals take the tetrahedral, divide it, and you get this energy. And you could convert that energy to a wavelength. And you'd say, like, you have white light, you'd subtract that wavelength, so it's absorbing green, so it absorbs green, so the thing would be red, like it would glow red. And this would be like probably in solution because this anion, right? So this would be an aqueous solution of that metal salt, and it would be red. Or you could look at it and say it's red. You could kind of say what it was, I guess, if you wanted, but. So that's how it's, so this is obviously like a chemistry thing, right? Like you're working with water and a metal salt, you're getting the colors of it. So it's, but this tetrahedral octahedral is the same thing in the spinel. Like we had two states for the metal, tetrahedral, octahedral, and they're transition metals in it. So it's the organic chemistry, inorganic chemistry, and the metallurgy are like linked together. They aren't independent subjects, you know. All right, so let's see what else. So that's just kind of some rules of the game on it, and that's the spectrochemical series. So this is where, so none of that is in the book. Like none of that stuff is in the book. That's all from it. But in the book, he just says like, here's the series. He just talks about lattice energy, and then for transition metals, he says they're stabilized due to d orbital splitting, which means exactly like you get those two energy levels for the octahedral, right? So that's, but he just says this, and like you don't know what he's talking about. So you have to kind of go back and figure out. Anyway, so then like this is just showing that the kind of the energy levels for tetrahedral, octahedral, and then and he's just mapping out how that works in crystals. You know, so like why does magnesium have this lower energy? It's because of this energy splitting thing going on. So anyway, 643. Let me just see if there's anything else to say here. Yeah, so anyway, so the homework will be something like this business, like zeolites, and kind of how, anyway, we'll go through that tomorrow and Thursday. I think we're ready to do that. Like I said, there's a lot in this chapter, so it's probably like 2 weeks of things. Maybe not. Maybe we can zip through that. So I'm up to 43. I'll quit there. That's good. Thanks. So I'll start at 43. Write it down. Any questions, anything? Or so yeah, the homework's on the MOF's metal organic framework stuff. So should be kind of interesting. I think, was there a seminar on that? Or there's one coming up in mechanical on MOFs. So we'll go through it here in that paper, and you'll know what they're talking about, maybe. Or at least you have it won't be totally unfamiliar, you know. It's one of those areas that's like popular, you know, it's kind of a popular thing to do right now. And again, it's like a mixture of materials people and organic chemistry people. There's a guy from Purdue. You sure he didn't come yet? Because I think I skipped it, but all right. You guys go to seminar, right? Okay. All right. Well, he'll come up soon. Maybe it's this week even. I don't know. Oh, it wasn't? Okay. Maybe it's someone else. Yeah. What did the Purdue guy do? Oh, okay, yeah. Oh, well, we covered a paper on that. Yeah, so we got that. That's good. There is someone doing MOFs though coming up. So, yeah, I missed that seminar, but I don't know. Anyway, so, all right.